Good afternoon, everybody. Good morning to some, maybe good evening to others. Thank you for joining us on the Designing for Durability webinar regarding dynamic performance of additive manufactured components in industry. So I'll just introduce what's going on today, some housekeeping. So with me today, alongside me is Rebecca Rife Musgrove, our Electropulse Business Development Manager. And also in addition today, we have Dr. Pete Bailey, our Principal Materials Scientist. A few requests, please. We will be recording the webinar. I hope that's okay for everybody. We'll also be doing a Q&A session at the end of the webinar. So by all means, as we go through, please type in your questions into the chat box or however you wish to get it to us. We'll go through them at the end. We should have a decent amount of time in order to do that. In our previous webinar, we had lots, so we encourage everybody to keep asking as well this time. And then finally, just to let you know, we will be posting the webinar on our YouTube channel. Again, the request we had last time was to share the content, either presentation. We will do that in due course, and we'll share that with everybody as well. So be rest assured, you can all just sit back, listen, focus, and ask away with regards to those questions.
Thanks, Mark. So I'm Rebecca, and I will be talking us through this webinar on designing for durability, dynamic performance of additively manufactured components in industry. So what I'm covering today is first some additive manufacturing fundamentals. So this may be a slight repeat of what we covered last time, but we really need to start with the fundamentals of additive manufacturing and their microstructure before we can then go into optimizing dynamic testing in industry, and then, as Mark mentioned, the question and answer session. So again, as a refresher, why are we discussing this now? Additive manufacturing, it's an industry that's been around for a fair bit of time now. It's obviously still got lots of new growth in it and growing all the time. And this is one of the main reasons we're talking about this. Market predictions is that the addressable market will go from around $30 billion now at rates, depending on your source, anywhere from 20 to 30% annual growth rates, to an estimated $90 billion market in 2030. So that's huge growth over the next 4 years. And this is, of course, being reflected in the testing market as we see it at Instron. And then why it affects us so much in the testing market is that we are now seeing this shift from prototypes, additive manufacturers being used for prototyping, to serial production use for additively manufactured parts. So it might be familiar to you here, for some of you that work with additively manufactured parts. We've got an example of a data sheet, and these are becoming more and more important, that when we print a part, we don't just want it to look like a certain part, so a prototype. We really want it to have mechanical strength. So we care now about those ultimate tensile strengths, the yield strengths, the elongations, etc. But if it was just prototype to production, I'd be sat here talking to you more about our universal testing machines and the static, tensile, and compressive tests. However, I work with the fatigue market. And so the reason that we in the fatigue market are talking about this is we're seeing this more and more in structural usage. So last time we spoke about additive manufacturing being used in Airbus planes. This time, another example, we're using it in implants. So we interviewed some professors at TU Dortmund this year, and they said that with additive manufacturing, we now have the possibility to create new geometries, for example, lattice structures, where we can exactly adapt the stiffness of the implant. And of course, that implant is going into the body. It is being used structurally. We definitely would not want that to fail over long-term loading. So we need to understand the fatigue properties across various industries. And then a refresher for those of you of just what additive manufacturing technologies there are and what it is. So as a reminder, additive manufacturing, or commonly known as 3D printing, is the process of creating 3D objects by building them layer by layer, often from digital designs. It uses a wide range of technologies. So on this side, I have an example of all the different types of technologies. So you may be most familiar with the material extrusion, so fused deposition modeling. This would be your typical benchtop 3D printer that squeezes out polymer filament and builds up layer by layer that you might even see in a personal lab. And then we get on to many other technologies, powder bed fusions. So this is laser mounting, laser sintering, that of photopolymerization, material jetting, binder jetting. And these are all more increasingly industrial processes that we're seeing in additive manufacturing. We also, not only are there a wide range of technologies, they also then use a wide variety of materials. So again, as I said, the most common that we saw was polymers, but we now see metals, ceramics, composites, and more. So some of the key benefits include the reduction of material waste in building, much faster prototype and design flexibility, and also, as I said here, the ability to create complex geometries that are often difficult and sometimes impossible to achieve with conventional methods. So in the last webinar, don't worry, we're going to get onto something new soon. The last webinar, we touched on the microstructure of additive manufacturing parts and how they affect fatigue testing. So we talked about defects and how they can cause premature cracking. We talked about the variability across parts, the anisotropy, so that means the differences in direction, and also the size effects and how often things are much smaller with additive manufacturing. And this webinar, and so if you're interested in that, you can go and watch webinar 1 if you haven't already. And this webinar, we're going to be talking about how those fundamental things then translate to some more problems and challenges in industry. And before I get into the industries, a general note on the implications for fatigue testing across all industries. I really want to emphasize that, firstly, in many ways, it is none. A fatigue test is still a fatigue test, and I really don't want us to lose sight of that. It's defined by a stress ratio, often known as S, and a number of cycles to failure, often known as N, and you can build up the SN curve. The reason we talk about it, and we talk about additive manufacturing in fatigue so much, is that because those defects beneath or often on the surface, we get differences in microstructure and production that change the properties. And realistically, ultimately, we often see the fatigue strength decreasing. So this is definitely something we need to test for and know about before using these parts in industry and in structural use. So I'm going to go through a few different industries, first talking about why we care, some different types of testing, and then I'll pinpoint a few points that we see in Instron as ways of optimizing the testing in those industries. So automotive, why do we care there? Many sources of dynamic loading. So these are things like engine vibrations, but also uneven roads. I think shout out to the UK roads here with all their potholes at the moment. My car's definitely getting a beating. And then thermal cycling, so when things heat up and cool down, they also expand and contract. And then crashes. So interesting to hear, I've talked a lot about fatigue, but if we take a step back and talk about dynamic testing, a crash is something that is very dynamic, very fast, is not necessarily the same as a typical quasi-static test. So this translates into many different types of tests, and this is not an exhaustive list. This is just some of the main ones that we at Instron see to do with automotive. The first being typical life testing. So this would be your standard fatigue test, so cycling load to determine properties. Generally, it involves plotting an SN curve as well, but it can also just be proof testing if people want to make sure something will last a certain amount of time. Something we typically see in automotive with live testing is people are doing a lot of testing to build up something known as a materials database. So how their material responds over a whole range of stresses, over a range of perhaps different temperatures or different humidities or different heat treatments, so that then design engineers can take that database, look at their car and work out which material to use. The second type of testing is dynamic characterization. And this, when we describe this, we're talking about cycling the load to determine material properties. So this can be things like the dynamic stiffness or elastic properties. The reason we see this a fair amount is we get a lot of polymers in the automotive market. So if you think about your car, there are a lot of polymer components. One that perhaps strikes me in particular is the polymer and rubbers in your tire, for example. And of course, those are, as they're rotating around, they're experiencing different stresses as they move. We did do a webinar focusing on polymers in automotive. So again, shout out to that webinar. And if you're interested particularly in polymers for automotive, that was a webinar done by my colleague Pete, who will be joining us for the Q&A today, and Stephanie as well. And then a final test type that I'm not going to talk through today because again, it was covered in the automotive webinar that we did beforehand, is high-speed testing. So these are often high strain rate tests to simulate crash conditions. So there is a photo here of our VHS, or very high, I'm going to get it wrong, strain or speed, depending on who you talk to. And so they can precisely control the strain rate, so you can do strain rate testing. We also have drop towers as well, where you can control the initial velocity or energy of an impact. So what I'm going to focus on today is particularly the life testing part of automotive testing. And as I mentioned, what we generally see at companies there is building up these materials database. So what we're trying to do here is optimize throughput without impacting results. So if you imagine you're building up those materials database, that is a lot of testing. Each individual SN curve might be up to 30 specimens. And then if you're doing that over a range of different conditions, alloy types, heat treatments, you can see that your testing burden quickly rises. So what we want to do here is minimize, firstly, the post-processing. So something we see a lot here is utilizing live calculations. The reason I flag this in particular is because we see a lot of data scatter. Again, I mentioned this in my first webinar with additive manufacturing. And so we've seen, and my colleague Pete Bailey will talk to this in a more detailed technical webinar later in the year, but we saw a lot of stiffness from doing a lot of data scatter from doing testing on some very small additive manufactured parts with very small cross-sectional areas. And one way that we were able to normalize and reduce that scatter was actually utilizing the dynamic stiffness measurements that we had throughout the test, so that we could then normalize the results for their actual cross-sectional area rather than the measured cross-sectional area. So that's just one example of how live calculations can reduce the post-processing requirements by having these calculated channels that are recorded during the test. So that's something, again, Instron have come in to fill the gap there, and we have a calculations module in our Wave Matrix 3 software. Not only does it do dynamic stiffness, a whole host of live calculations for that dynamic characterization that we spoke to as well. The second thing here is frequency effects. So again, there was discussion last webinar about what frequency to test materials at, and the same question applies to additive manufactured materials. And with automotive, where we're testing a lot of polymers, if we increase the frequency, we can adversely impact the test results if they have self-heating. So sometimes you think if you stretch a rubber band a lot and very fast, it might heat up. So we can't just run these tests as fast as we want to build up these materials databases. What we can actually do is minimize the effect of these frequency effects by monitoring the temperature directly and modulating the frequency. So instead of having to slow down the test to maybe 2 or 3 hertz and spend a lot of time building up our materials database, We can instead monitor that temperature, increase the frequency as fast as we can, and then lower it if we are starting to see self-heating. So aptly named, this is the specimen self-heating control module. So there's definitely a lot of industry currently looking at the effect of self-heating. There's currently a campus project looking at formalizing and standardizing how we can counter for frequency effects. So that is just a few ways of optimizing testing in automotive. Continuing our whistle-stop tour, we'll go to aerospace testing. Again, why does it matter? Think about in a plane, there's a lot of vibrations there, especially during takeoff and landing, where the wings especially will move up and down. And then additionally, that thermal cycling, especially in the engine on startup and cool down. Test types we see here, again, we're going to see life testing, that typical fatigue test, that we still want to have a materials database in aerospace so that we know what materials to use in our plane and plot the SN curve. But then we get to some more speciality tests that we mainly see in aerospace, and those are fracture toughness and crack growth rate. So fracture toughness is standard defined testing to determine often the energy of fracture for comparative reasons. And crack growth rate testing, as the name right suggests, is cyclic testing to analyze the crack growth rate. These tests are quite specialized, so I wanted to, in case any of you aren't familiar with fracture or crack growth testing, just do a quick summary here. So fracture toughness, it's a property of the material, just like a tensile strength or a yield strength. And it is generally describes the resistance to localized failure. So rather than a bulk tensile strength, it is localized crack growth or crack failure. The tests are conducted generally by introducing a single crack from a pre-machined notch. So we already kind of damage the specimen by having that notch in there that you grow your crack from. And then we have three main test types from that. We have fatigue crack growth rate tests, otherwise known as DA by DN, and they determine how a crack grows under high cycle fatigue conditions. We have brittle fracture, also known as K1C fracture toughness, where you then pull apart the sample and it has a brittle fracture, and the result that you get from that is a critical load for the fracture. And finally, we have ductile fracture, also known as J1C fracture toughness. And here it is, as the name suggests, more ductile, and we repeatedly load the crack to gradually tear it open. And what we measure here is the energy for fracture. So how do we optimize those tests? Well, perhaps even more important than throughput, although throughput is always important to all of the industries we work with, we want to optimize testing by ensuring standard compliance. So aerospace is a very standard-driven world. You want to make sure you're always meeting compliance requirements so that your plane is allowed up in the air and your parts are allowed in the plane. So two different compliance that we consider here. First is alignment. So that's something that's often quoted that is needed for NADCAP compliance, although many individual ASTM standards also have requirements on the alignment as well. The reason it's so important with additive manufacturing is that crack resistance varies very significantly with orientation. So if you are off axis, you have a very high risk of off axis cracking, as it's much more sensitive to alignment in your fracture testing. So before testing, we need to make sure that samples and machines are aligned, and the way that we do this is using a strain gauge specimen to measure the bending forces and how much bending there is. Again, this is something Instron has a solution for, and what we use is the Align Pro kit, which allows the user to adjust the angular or axial alignment to ensure that we have a perfectly aligned load string for compliance. The other part is validation. So I've put here validation for brittle or ductile standards. So if I mentioned before, we had the K1C and J1C tests. So with a brittle sample, such as aluminium or titanium, what we've seen experimentally is that you can sometimes see reduced linear elastic behavior with these, so they become less brittle. Whilst in high strength steel, which are reasonably ductile, we actually sometimes see them have lower ductility. So we often can't predict exactly whether the ductility will increase or decrease when you additively manufacture a sample. The challenge that this introduces for industry is you then challenge the validity of your tests. So if you think about ASTM E399, which is the brittle fracture test, there is a check in that to check that you have truly brittle fracture. It checks the ratio between they've got a 0.2% offset load. So what we can do again with Instron solutions is in blue hole fracture, we calculate and check the validations automatically. So as soon as we do a test, it tells you whether or not we hit those criteria. Was that test indeed brittle enough? Or whether we're out of validation. So making sure that once you've done the test, it is in fact compliant and that the additive manufacturing process hasn't made the material non-compliant for the test. The final industry I'm going to talk about is medical device testing. So there's lots of sources of dynamic loading here. And these perhaps are easier to visualize because it's simply your movement, walking, jumping, but then also the beating of your heart and your muscles contracting. There's a lot of dynamic loading within the medical device world. And of course, we do not want anything to break inside our body. So the test types that we're going to talk about here, you'll notice life testing is in all of these industries. It's the bedrock of fatigue testing, so cycling loads to determine the fatigue properties, plotting an SN curve. However, there's a subset of fatigue testing that is much more visible during medical device testing, and that is proof testing. So this is still cycling the load, but it's checking whether specimens basically pass or fail a specific life requirement. So the photo I've got here, if you can see it, it's very teeny tiny, is our 16-station electrical system. So if you have a life or a proof testing requirement where you need to pass or fail a specimen, generally you can't just pass one of them. You tend to need to prove that quite a few of the devices that you've manufactured will pass those requirements so that the FDA will sign you off. That leads to you having to test up to 28, 30 samples at a time. So this and have them pass. So the 16-station test system means that you could test 32 at once on 2 different machines and therefore hit that requirement to have that 30 samples with a little room to spare in case some of them fail. The final type of testing is multi-axis testing. So again, if you think to your body and how you load it personally, if we want to simulate that body loading, you're not just loading uniaxially. There's often twisting. So all the way up your leg, you can imagine, especially if you play sport, you might pivot on the spot. If you turn around, there's a torque being induced into your ankle, up towards your knee and your hip as well. And same with your shoulder or anywhere else. So when we think to medical device testing, what we want to optimize here, and again, of course, throughput, of course, standards, we want to meet standards, but the one that I'm highlighting here is replicating real world conditions. So we want to have essentially representative testing. But then if we think about when we test, often we just test a coupon, as properties might vary with geometry or be altered with surface conditions. Actually, we want to test a specific part. So if we think back to the first webinar where we spoke about how additive manufacturing parts can vary because of the local thermal heat dissipation. If you have a very skinny bit that you've just printed, it's very easy for the heat to dissipate. Whereas if you have a very thick piece of material that you've just printed, it's much harder for the heat to dissipate, so you get different heat properties. We don't want to just test a coupon, we want to test the full part, as those properties might vary. So that's the representative size or coupon, but then there's also the representative environment. So again, we think to our body, it's not necessarily ambient air that we want to test things in, we might want to test in a saline bath. So at Instron, what we did is in all of our electrical systems, we make sure we have a corrosion-resistant T-slot table, which you can affix, and in the photo you can see here, you can affix a biobath to it to test in real world parts. And then at the top, we combine it with our Dynastyle load cell. So a load cell that is allowed to move and can actually compensate for inertial forces, rather than forcing that load cell to be fixed below a very risky bit of fluid that you would not want it to spill onto. So that is the samples, and then we move on to the axis. So as I mentioned, representative conditions for medical devices are unfortunately not just uniaxial, they are multi-axial, and most components will experience torsion. And in fact, often that torsional axis is the weaker part. So if you imagine fixing an implant to your bone, when I was speaking to some medical device scientists, the strength uniaxially is generally okay, but actually often when you move it torsionally, you end up shearing the implant from the bone. And then beyond that, we also have the layer by layer structure that can also impact shear strength. So this is harking back to what we spoke to about anisotropy, so differences in properties in different directions. So what did we do about that? We made sure that the electricals had linear and torsion models so that we can do multi-axial testing to represent the real world conditions. So as a summary of the solutions for these different challenges, the first is having specialized systems. So we have the electricals linear torsion models to do multi-axis. We have the electricals 16 station systems to ensure we can pass and fail multiple samples. And we have high strain rate systems such as the VHS for automotive crushing. We have high accuracy load cells. So not only can we measure accurately across the full range of force, but we can also compensate for inertia and move that load cell wherever we want to. A lot of the capabilities in the software. So we have advanced software, wave matrix 3, Blue Hill fracture, or Blue Hill universal, to make sure that we can add those calculations that we talked about in wave matrix 3, or those validations in Blue Hill fracture. And then finally, the expertise. We've been working in the materials testing industry for 80 years. We follow these standards closely so that as industries continue to adapt, and of course we're seeing a lot of adapting with additive manufacturing at the moment, we can continue to keep up with the solutions that are needed.
So additive manufacturing testing, it's surprisingly still early days relatively in the material testing world. Still many challenges to overcome in the industry. We will continue to provide webinars and information from our viewpoint with regards to this field, and we'll talk about some upcoming webinars in a moment. As I mentioned earlier, we are recording this webinar. We'll post it on our Instron official YouTube channel. We'll also follow up with an email to you all with a link to that. And then also for some further information, we did a case study on additive manufacturing at TU Dortmund. This case study is revolving around bio applications, biomedical, where the university started off studying dental implants and then moving over to dental structures. I won't ruin the story, but what's very interesting about it is the technology they're using and the development they've made with regards to using bio-resoluble magnesium materials. So I recommend having a little watch of that. And then finally, webinars coming soon. So we've completed webinar number 1. Will be available soon. And again, we'll send that out in the show notes afterwards. We've just done webinar number 2, Designing for Durability. Those were both held by Rebecca here. And then moving forward, we are due to advertise the dates, one in August, I believe, late August, and number 3, that is, around fatigue data and miniature specimen effects in additive manufacturing. That will be hosted by Dr. Pete Bailey. And then the final one, also hosted by Pete, will be fracture toughness measurements on additively manufactured materials. And this will be shown in September time. So we'd love to see you all there, and we'll send out invites on social media and also via email. So do not hesitate to look out for those. And on that note, I just want to say thank you to you all. I hope you have a wonderful day, whether that's an evening or the rest of your day, because it's in the morning where you are. Thanks from us at Instron, and I'll see you later. Goodbye.
Thank you.